Hello, I am Sambit Giri. I will talk about the Halo model approach to model the 21 centimeter signal. This work has been done in collaboration with Aurel, Timothy, and Jordan. There are two key goals of this presentation. First, giving an overview of the Halo model. Second, modeling the 21 centimeter signal at the cosmic dawn. Before I talk about the Halo model, let me show you the picture of the evolution of our universe. In this picture, time goes from left to right. After the era of the cosmic microwave background radiation, there was no source of light, and therefore the universe was dark until the formation of first galaxies. Once the first galaxies formed, they emitted photons that heated and ionized the gas in the intergalactic medium. The time when the first galaxies formed and heated the gas in the is known as the cosmic dawn, and this is the era I am interested in for this talk. Hydrogen is one of the most abundant element in the intergalactic medium. One of the promising observable is the 21 centimeter signal, which is produced by the spin flip transition in the neutral hydrogen. With this signal, we can observe the hydrogen present in the intergalactic medium during the cosmic dawn. The 21 centimeter signal from this time is redshifted and found at the radio frequency band of the electromagnetic spectrum. The radio telescope will observe a quantity known as the brightness temperature. The equation here shows that it depends on the neutral hydrogen fraction, the spin temperature, and the baryon density contrast. The spin temperature depends on the temperature of the gas during this time. Here I show the sky averaged 21 centimeter signal evolving over time. There are many codes to model the 21 centimeter signal, and each of them can be broadly put into these categories. The N-body plus RT and radiation hydrodynamical code are accurate, but computationally very expensive. The analytical and semi-numerical codes are less accurate, but are very fast and therefore useful for doing statistical inference of observations. In this talk, I'll focus on analytical methods to model the cosmic dawn. For more than a decade, only excursion set-based methods were used to analytically model the 21 centimeter signal. In a simple picture, in excursion set-based approach, we look at a location and try to figure out what impact the photon sources in its surrounding have had at this location. In this talk, I will extend the library of analytical approaches by introducing a halo model based approach. In halo model, we look at photon sources and try to figure out what impact these sources have on its surrounding. Let's look at the power spectrum, which is the Fourier counterpart of a correlation function and gives a measure of spatial fluctuations in the signal. The power spectrum in the halo model is given by two terms, which are the one halo term and the two halo term. The one halo term is given in this blue box, describes the correlation within the halos. And the two halo term describes the correlation between locations inside two different halos. Let's now look at the ingredients needed for the halo model. Uh, One of the ingredients is the halo distribution. The distribution of halos is described by the halo mass function. The next ingredient is the amount of photons emitted by the sources. Here we parameterize the amount of photons emitted by sources using a mass dependent quantity, which is this F star. We also need the halo bias, which is given by this equation here. And lastly, we need the flux profiles, Ux and Uy in these equations. We determine the flux profiles for different halo masses at every redshift. Here in the two panels in bottom left shows the flux profiles in real space, and the bottom right panel shows these flux profiles in Fourier space. Finally, we construct the 21 centimeter power spectrum from the power spectrum of each of the components, such as Lyman alpha coupling, heating, and distribution of baryons. This equation is derived by linearizing the brightness temperature equations. Each of these power spectra components can be derived using the Halo model. With our framework, we can reproduce the generic behavior of the 21 centimeter power spectrum at cosmic dawn. In this plot, I show the evolution of the 21 centimeter power spectrum at three different wave numbers, K values, over different redshifts. In this plot, we can clearly see two peaks in the power spectrum. The first peak represents the Lyman alpha coupling, and second peak corresponds to the X-ray heating. What else can we do with our framework? We can explore the nature of dark matter by analyzing 21 centimeter signal with our framework. One of the non-cold dark matter scenario that we can explore is the warm dark matter scenario. Here I show the halo mass function for the warm dark matter scenario. The solid curves here correspond to the halo mass function for cold dark matter, and the dash dotted and dotted curves represent the halo mass functions for warm dark matter scenarios for two different mass values. We can clearly see here that the warm dark matter scenario, in warm dark matter scenarios, the structure formation is suppressed at small scales. Therefore, we have fewer small mass halos in warm dark matter scenarios. Let's first look at the impact of different dark matter scenarios on the sky average 21 centimeter signal. The black curve here represents the global signal for the cold dark matter scenario. If we keep the same source model and change the nature of dark matter to warm dark matter, then we get the blue curve. From this curve, we can see that the structure formation is delayed in warm dark matter scenario. Therefore, the absorption feature moves to smaller redshifts. We also explore another model for warm dark matter where we keep the mass of the warm dark matter same, but change the source model such that the global signal of this warm dark matter scenario matches with that of cold dark matter. And this model is shown with the orange line here. Then we put this warm dark matter scenario into our halo model and get the power spectrum. Here the three panels show the power spectrum at three different redshift. The x-axis in each of these panels gives the wave number. Uh, Here, the shaded gray regions represent the error bar due to noise in upcoming SK observations, and these noise correspond to observation time of 1,000 hours. Here, we can see that the power spectrum are different for the different models, and we can distinguish between these models uh, using these power spectra. Finally, this brings me to the end of my talk. So I showed that the Halo model gives a very fast analytical approach to model the 21 centimeter signal. With this fast approach, we can explore the parameter space, and this is useful while interpreting our 21 centimeter observations using Bayesian inference methods like MCMC. I also discussed how we can model non-cold dark matter scenarios using the Halo model. Thank you.